Can you hear me? Okay. Hey, everyone. So my name is Laurent. I work at Kyutai, and today I'm going to tell you about how we use Rust to build and deploy Moshi, a state-of-the-art speech-to-speech model. Okay, so first thing, let's talk a bit more about Kyutai. We're a not-for-profit research lab. We are based in Paris, and we started activity at the end of 2023, so something like a bit more than a year now. We released Moshi, we announced Moshi in July last year, made an open source release back in September. Then we published Helium 2B, which is a small text model, at the beginning of this year. And a couple of weeks back, just before the AI Summit, we released Ibiki, which is a French to English translation model. So it's all speech-to-speech. It tries to keep your voice. I will not be using it today because it works fine, but still there are some hiccups to fix. We're all about open technologies, open research, so we are not for profit. We publish everything, and obviously open source. So we're gaining a lot from the open source, and especially from Rust, and we like to publish everything. So most of the things that I will mention in this talk are already open source. Some might not be because we are still polishing them and wanted to publish them. Let me know, by the way, if I mention something that is not open source and you think will be helpful for you. So now a bit more about the tech stacks that we use. So we are not a pure Rust shop. We are doing research mostly in Python, and if there is a big takeaway for my talk, I would say that Python is actually a great tool when it comes to doing ML research. So if you want to do fast iteration in a notebook, you should probably use Python. You can use PyTorch and Tch-rs to do your machine learning modeling, and it's pretty amazing. But that doesn't mean that there is no space for Rust. And we've been using Rust at quite a few places, actually, and I will detail them a bit more in this talk. So a first obvious place where you want to use Rust is when you productionize a model. If you try to productionize a Python model, it's very annoying because you have to deploy a whole Python environment with tons of dependencies. You're talking about gigabytes of not the model weight, but just the binaries that you ship around. You will have a bunch of efficiency issues. You will suffer from the GIL, even if with the latest Python, it's less of an issue. You will have some overhead around like pretty much every single caller. So that's why Rust is actually great for making production version of models, and all our production stack is based on Rust, as we will see later in this talk. Rust is also a great fit to interface with Python in the research process itself. So when it comes to running the training of our models, we will use Rust to actually do the data loading in a multi-threaded way. We will use Rust also at a bunch of other places that I will not really detail in this talk. Like here I've mentioned that we have a way to visualize our audio data sets in a web browser, and that just works all in Rust. Same cluster monitoring, it's actually all in Rust, and the very big upside of that is that it's rock stable. You can just let it run for a year, and you never have to touch it. So first, I will detail a bit what is a speech-to-speech model. So bear with me for the first few slides. There will be almost no Rust and lots of machine learning stuff, but hopefully it will be interesting. So as I mentioned, we announced Moshi back in July last year. It's a conversational speech-to-speech model, and it takes audio as inputs and produces audio directly without using an intermediate text representation. So the nice thing with that is that the model will hear your intonation and will also be able to produce different intonation. It's not going through a text bottleneck that will limit the amount of information that you can exchange with the model. Moshi can be tried online on moshi.chat, and the code and weights are available on GitHub. You have a Rust version for the inference platform, and if you use moshi.chat, it's actually some cloud GPUs that are running Rust code that will power the thing. So common questions that we have is, why are you trying to build a voice assistant? It already exists, and it has existed for 10 years or something like that. And it's true that you have things like Alexa, Siri, Cortana that have existed for 10 years maybe, that have millions of daily usage. However, if you use them, you probably feel that they're a bit off when it comes to actual language. It doesn't feel like talking to a real person. It only works in very, very specific scenarios. And we wanted to push the thing a bit further to have a natural interaction with the users. It's a bit like the old chatbots when it comes to text. Like before ChatGPT, chatbots were really, really dumb, and interacting with them was about finding the right keywords to trigger the right thing. And we believe that it's a bit the same for voice, that before it used to be complicated to use a chatbot, and with the new generation of model, so Moshi, but also the latest voice mod for GPT-4o and the project Tch-rs from DeepMind, the communication will become more and more natural. So the main reason why the communication is not that natural with the existing assistant is that they use what we call a cascading model. So you actually go through a different number of steps to process the user input. You will first have a layer that does voice activity detection. So the model will try to locate that you're speaking, and when you stop talking, it will trigger something so that it can process the speech that you've produced so far. This speech, it will use some form of automated speech recognition engine to actually convert it to text. This text, it will feed it right now to a large language model, because large language models for text are pretty good. That will spit out some text, and then you pass this text to a text-to-speech engine, and you're back into having some speech that you can serve to the user. Obviously, that's annoying because it takes a bit of time, like you're talking about 3 seconds to 5 seconds, maybe a bit more, depending on how well it has been optimized for. And also, as I already mentioned, you're losing a lot on like the emotions that voice can carry, the speaking style. Like you cannot really use that just asking a voice assistant, how do I sound today, or where my accent is from, or help me give better talks, or that kind of thing. Another limitation of existing voice models is that they're mostly half-duplex. So I mentioned that there is a form of voice activity detection to locate when the user is speaking versus when the model should be speaking. And that means that it's a bit like a walkie-talkie. So only one person speaks at a time, either the user or the model. Whereas if you have a conversation with someone using a phone, you will have some overlap. People will tend to say things at the same time, either finish the sentence of someone else or start answering because they know from the context what the person is meaning. It's evaluated to something like 10%, 5% to 10% in English of the speech is actually overlap. And in other language like Japanese, it's actually a lot higher than that. So again, it makes things more natural that you can still talk and the model can just say or whatever, and the other way around, if you say you don't want the voice activity detector to trigger and to just stop talking because it thinks that you're going to make a full sentence at that point. So yeah, Moshi is trying to just get around all these difficulties, and we'll see in the next section how we're actually making that feel a lot more natural. So the first step to do that is to actually perform audio tokenization. So we compress the audio signal into a set of discrete tokens. So you already know probably codecs like MP3s that do audio compression. Here we're talking about a compression that is a lot more aggressive than that. The compressed audio stream will be something like 1 kilobit per second. So we go from having 24,000 values that are sampled per second, which is a usual frame rate for audio, to having values at 12.5 Hertz, so 12.5 times per second. And we have 8 values that are given per second. So these values, actually, you have an increasing level of detail. The first value represents really what you say. The second is more about your intonation and so on. And the last one is probably just the acoustic characteristic of the room or something that you really don't care that much about when it comes to interpreting the language. So all that is done with a neural network, but it's actually a pretty small one. You can get it to run in the browser with WASM, like the Rust implementation. It doesn't run on a phone in the browser if you don't have the latest iPhone, but on a laptop, it's not a problem at all. And yeah, with that, the nice thing is that you're going from thousands of values per second to 100 tokens per second. And these tokens also are discrete, which means that now you can use the transformer architecture, which is what every large language model is doing. And the nice thing is that over the last couple of years, people have become very, very good at using transformers to model any discrete task. And yeah, that's how you feed these audio tokens into, again, this big transformer thing. It's not, we don't feed them directly like the 100 token per second, because it's actually hard to do that efficiently on the size of models that we are looking at. We're looking at a model with 7 billion parameters. So instead, we will feed the token 12.5 times per second and give 8 of them at that time. We'll have a big transformer that will process this chunk of data. It will produce some embeddings, and then it will have something that we call the depth-former, which is a hierarchical transformer that will produce the 8 values that the model has to output per second. So that allows you to train a model on lots of audio data. We're talking about millions of hours of audio. And it turns out that if you do that, the model will learn to predict the next token. So it will learn to complete things, same as GPT. So at first, it will learn what language is. And at some point, when it has seen enough audio, it will start to learn about reasoning and be able to carry small operation. It's not that smart, but still, from audio, it's able to learn quite a few things. So the first thing we will look at now is actually a prompt. So that will be some audio that we will feed into the model. It will be actually the brown part that you see here. We'll just inject some data, and we will let the model predict the next thing. So here is the prompt that we will...
Listen to your sister, Morty. To live is to risk it all. Otherwise, you're just an inert chunk of randomly assembled molecules drifting.
Okay, so that's just some random audio. And now the model will take that prompt and try to predict what is the most likely audio after that. It will play the prompt again, so you will hear the same beginning, and after that, it's just the model that says, oh, the logical continuation is that.
Listen to your sister, Morty. To live is to risk it all. Otherwise, you're just an inert chunk of randomly assembled molecules drifting in the gases in a vacuum of space-time. Live and love.
So you can see that the model understands the concept of voice and try to preserve the voice, and also understand a few concepts and what should be logical for a continuation of that thing. So if you want to generate random episode of Rick and Morty, you can try just continuation of the model. Though it's not that good after tens of seconds, it might do a bit of a weird things. Okay, we have a continuation model now. So it's the GPT brick of ChatGPT, but it's not a dialogue model. So the last step before we can actually communicate with the model is having this kind of two-person interaction or this dialogue thing. So it's what is called the instruct step for text model. And here we do it a bit separately. We do what we call multi-stream, meaning that there is a stream of audio tokens for the assistant and a stream of audio token for the user. The nice thing about this is that the assistant will speak continuously. So it might just produce silence when it's listening to you, but it's actually producing audio. And you will speak continuously. So whenever the model is speaking, if you start speaking, the model still listens to you and will totally hear what you say. Okay, and so that we train it on actually tons of synthetic data that we generate via some text-to-speech system. So here you see the gray bits are actually the user. This part is not predicted by the model. It's the input from the microphone of the users. But when we actually do training, we train the model to predict them too, because it makes the model a bit more efficient. And also it means that the model learns about predicting the next things that you're gonna say. So it can infer from the beginning of your question what is likely to happen next, and it can start answering a bit in advance thanks to these capacities. So that's it for the modeling part of the thing. Now we're going to see how we're using these models when it comes to actually interacting with them in real time. The thing is that there are no well-defined metrics of quality for these models. You really want to try them out and to get a sense of how well they do when you interact with them. So we had to build a real-time inference engine that let us interact directly with the models and try it in real-world situations. And for that, we use obviously Rust to do that. And we built what we call the Moshi station, which is a computer that sat in the middle of our office, and on which you always had the latest model available to you. And you can just use it and play a bit to see how well it goes. We'll see a few demos of that later. So at that point, we're talking about April or May last year. We didn't have the multi-stream. So in the first video that we will see of the Moshi station, the model actually, you still have to do the end of turns explicitly. So you will see Alex actually hitting the space bar because he has to tell the model, oh, actually, I'm done talking. And later on, we developed the technology so that you don't need that anymore. So yeah, let's look at the video. And yeah, just to mention, so like obviously all the inference is done in Rust, but also the terminal UI, it's done in Rust, and it's based on Ratatouille, which is a pretty nice framework to use.
You speak like a pirate.
Oh, you mean in a thick southern accent?
Yeah, exactly.
Like, I'm a southerner, and I know how to talk with a drawl. I mean, I know how to say y'all and thank y'all, and I can whip up a good old barbecue.
So you can see that Alex was pretty excited by the interaction, and the reason why is that it was the first time that the model was able to do like intonations and answering when you ask him, when you ask it, speak like a pirate, it will be able to do pirate voice because in its data set, it has seen enough of people doing pirates or whatnot so that it can replicate that kind of thing. So there are a few constraints for building a real-time model. The first one is around efficiency. So we mentioned that the tokenizer produces tokens at 12.5 Hertz. So you have to produce a new token every 80 milliseconds. And it's kind of a hard deadline. It's not a hard deadline as in someone will die if you don't meet it, but there will be an audio skip and it will be noticeable to the user if you don't produce the next tokens at that point. So you really want to have deterministic performance. And for that, having a language that would have something like a garbage collector would be pretty tricky because you don't really know when it will trigger, and it might trigger at a wrong point and just you would skip a frame because of that. So you also want to optimize the overall latency of the model. There is obviously the throughput of the model. You want it to be able to produce values, again, 12.5 times per second at least. But you also want to optimize the latency, or what is called the time to first token, because you want the user to say something and that thing to be taken into account by the model as soon as possible. And for that, the numbers that we get are around 200 milliseconds, which is ballpark like of a human being. So yeah, why do we use Rust for that? So Rust is pretty great for its cold startup time. So if you bring up a new inference engine, it will be there very quickly compared to a Python runtime that you have to bring up. You have pretty fast CPU inference, so it doesn't matter much for the main model here because we run it on a GPU. But for the audio tokenizer or that kind of thing, it's nice that you're able to actually offload that to the CPU and don't have to, that way the CPU can run the thing in parallel with the GPU crunching the big numbers. It also provides low and deterministic latency as well as memory footprint. So as everything is deterministic and based on where your variables go out of scope, the memory is released as soon as this happens. And it's pretty nice because you're kind of optimal when it comes to memory usage. It's especially useful for our models because, again, we are doing real-time stuff and we don't want to miss any form of deadline. Finally, the last upside is the easiness of deployment. So we just have standalone binaries that are statically linked, whereas if anyone tried to deploy Python models, it's usually a bit trickier to get everything right there. So we use PyTorch for the research. I would say we use 80% PyTorch and 20% JAX, but let's just focus on the PyTorch aspects for now. So a way that we could go around deploying our models would be to just train our models with PyTorch. And then the core of the PyTorch library, it's actually a C++ library. It doesn't involve Python. And you can just hook it directly to Rust via some FFI. So I started a project on that, which is called Tch 6 years ago, or something like that, back in 2019, I think. And it provides a way to do that. So in Tch, you actually have two different crates. One of them is provide some low-level bindings to PyTorch, and the other one, Tch, try to give you some more Rust idiomatic API around PyTorch. There are quite a few benefits from that, mostly that the benefit come from PyTorch itself. So you get some very nice kernels that have been optimized for all the NVIDIA architecture that you can think about. You will run very well on the CPU too. It will use Intel MKL or whatever under the hood, but it will be pretty fast on servers that have AVX 512 or so. It will cover lots of operations for lots of different domains, that is audio, but also video or whatever you can think of. So all that is pretty nice. And the biggest upside to me is that you also have a unified model view, like the model that you create on the PyTorch side. You can export it directly and use it directly on the Rust side. So for that, it uses something like Torch script, which you write from Python, and then you load the Torch script from the Rust side, and you can run it directly. You will still have to do the pre-processing and the post-processing on the Rust side, but there it's actually pretty good because it will be efficient. Another benefit that I listed is that you have backprop support, so you can do training too if you want, but here we don't care about it. Let's see a small example of Torch script. So on the top right corner, you see a model like that's ResNet 18, so it's a pretty old vision model that is loaded and saved as a Torch script module. So we just create this model.pt file, and it's a standalone file that will contain everything, the model architecture and also the weights. And then it's easy on the Rust side, that you can see on the other side of the slide, to load the model itself and apply the forward method there, which is like the hook that is registered by the model on an image. So with all that, you manage to export a model from Python, load it on the Rust side without having any form of Python dependency. So all that is working fairly well, like it has been stable since the first PyTorch stable release, which starts to be pretty old now, like I would say at least 2020 or something like that. And that would definitely work out of the box, but there are some limitations to it. The first limitation is that you still have a very large dependency. Your dependency is of the order of a gigabyte or a bit more if you want to have GPU support. And it's very hard to trim down the dependency so that it only embeds the kernels that you care about. You will have slow startup time, and that's mostly due to this very large dependency. Like you have to map this big file and recognize all the symbols that are in it. And you cannot do anything like running in the browser. It can be tried, but I don't think anyone managed to do it properly. Also, running on the edge will be pretty tricky too. So that's why starting from, I would say, it was middle of 2023, I worked on a framework called Candle. So this framework, it's called Candle because it's a smaller torch. And this framework is actually sponsored by Hugging Face. Hugging Face has been pretty good at publishing Rust crates to help with machine learning stuff. So the design of Candle is very different from what was done for TCH. It's a much minimalist approach to an ML framework, and mostly because it was done only by a few contributors. So we cannot afford to cover all the ground that PyTorch will be covering. In particular, we won't provide the best kernels for every single operation, but you will still be able to get decent performance for most kernel, and also to hook specialized kernel if you need so. So we have hooks for flash attention or for kubeless, which are the kernels where most of the time is spent in training and inference nowadays. We still want the app to be SIMD optimized and everything to run well on CPU because there is a big use case on the edge for this framework. And we also wanted things to run fast in the browser. So it doesn't mean that everything will run in the browser, but it's always good if you can offload a bit of the model in the browser. When it comes to Moshi, actually, if you run the tokenizer in the browser, the very nice thing is that you only need a bandwidth after that of 1 kilobit per second to transfer your audio tokens to the server. So you can use very, very poor networks. It will still work because the browser is helping you compress the audio data. And yeah, we also wanted to have a pure Rust implementation for as many operations as possible. So the things that are not well supported are bfloat 16, but all the rest should work well on CPU, not with the best performance in turn, but with good enough performance for most use cases. Yeah, a center type for Candle is the tensor type, and it's one of the biggest design decisions that has been made around it. Initially, it was totally immutable, but for performance reasons, now it's only almost immutable. It's possible to tweak it a bit, and that's useful for what is called the KV cache if you want things to be a bit faster. It's ref-counted and send and sync, meaning that there is some form of mutex around the tensor objects itself. So the idea there is that you have some overhead for each ops because of that, but each op should be something that actually triggers quite a few computation. So it should not be too much of an overhead when it comes to real-world models. Obviously, if you try to use it to compute values, like to make operation on scalar values or on very, very small vectors, then the performance will be bad because the overhead of the mutex will start counting. The tensor type is actually, so it represents this array of data, and we want for something that is super simple. So in the type itself, we don't represent anything. It's just a tensor, not a tensor of something. So in particular, there is no information about the dimension, and that's, I think, the case for lots of other ML libraries in Rust. But there is also no information about the device where the tensor is living. So it can be on the CPU or on the GPU or on different GPUs, because it's fairly common to have boxes with 8 GPUs when you're doing training. Or it can even be a remote tensor that is on a GPU somewhere else. And the last thing is that it doesn't even have information about the element types that are stored in the tensor. And that means that you can try adding two tensors together that contain different element types, and then it will crash at runtime. So the typer will not help you against that kind of error, meaning that it's easy to make the typer happy, but you have more errors at runtime, so there is definitely a trade-off there. One thing that makes it somewhat reasonable is that usually there is a single control flow in models. So if you make the model run once and you hook that in your test, you're pretty sure that it will not bite you after that. But still, it's an open question whether we should put more type information in the main tensor type. And yeah, one other thing about Candle is that we benefited a lot from the whole Rust ecosystem of crates, libraries, and good practices. So compared to what researchers will typically do when developing models, Rust forces you, it doesn't really force you, but it gives you all the good tools to have a proper CI that runs some decent tests, to have regression tests all around the place, to also do good performance analysis, and that means both benchmarking of your model, seeing where the time is actually being spent. You have things like criterion that are pretty good so that you run that multiple times and know if your improvement is actually an improvement or if you just change nothing. So it's nice that you can back your improvement by actual metrics. We also use tracing crate quite a lot because it helps you knowing where the time is spent in your model. So here I've put the output of a standard. I think, yeah, it's a unit, so it's probably coming from Stable Diffusion. And you can see that there is some form of transformer architecture. Most of the time was spent at that time in the softmax operation, which should not be the case, meaning that it was not well implemented at that point. A last big advantage of Quandle is its quantization support. So quantization is about, instead of shipping the full weights of your model, you ship an approximate version of the weight so that it's much smaller. And it's actually super helpful. So people have started using that more and more, I would say starting from 2 years ago or a year and a half ago. Because nowadays, model inference, it's mostly bounded by memory bandwidth and by getting your model weights from the GPU memory to the processing unit, or from the CPU memory to the actual, for the main memory to the CPU itself. So especially because when you run inference locally, you run with what is called a batch size 1. So you're just taking the weights, doing something with them, and throwing them almost immediately. And that's why having quantization actually helps a lot, because what you do in this case is having specialized quantization kernels that will run on your GPU. You will fetch from the memory the quantized weights, and only when they reach the CUDA units of processing, they will be expanded to a more floating type, and the processing will take place. But the memory bandwidth will be fairly limited. So for text models, it's quite common nowadays to do what is called Q4. So you actually use 4 bits per weight, whereas when you train the model, you use 16 bits per weight, and you will get a speed up. It's maybe not 4, but you will get at least 3 as a speed up. It's the case for text models, but for audio models such as Moshi, if you try Q4, the model is really becoming very bad. So we do more Q8 rather than Q4. But still, you have a factor of 2, which is a nice thing to have. So yeah, when it comes to Candle, I mentioned that we wanted to reduce the model latency, and that's where Candle actually was very helpful, and compared to PyTorch, was a lot easier to understand compared to PyTorch through TCH. It was a lot easier to understand where the time was actually spent when it comes to actual latency. So the theoretical latency of our model, it's 160 milliseconds, because the model has to see 2 audio frames before it will take the information into account. That's for research reason. That helps a lot the model learning to have some form of delay so that it can ground itself on some things in the past. But there is a trade-off there, which is around increasing the latency. And the achieved latency that we get, if you use the online demo, it should be a bit above 200 milliseconds. 200 milliseconds is more if you run things locally. So 160 milliseconds of incompressible latency, 35 milliseconds spent on the GPU, and something like 5 milliseconds that is spent at various places in the infrastructure. So that makes a latency, again, that is pretty good for human interaction. And when I say latency here, it's really from the time where the microphone records what you say to emitting the first audio packet that contains information that is influenced by this data. So it's really an end-to-end latency. Yes, so we're serving Moshi at scale on our cloud infrastructure. We did that because we're very happy to do research and build models, but we want lots of people to be able to try out our models. So we needed to offer a demo that is not, you should have an L4 GPU or a small GPU to run it, or a MacBook, because MacBooks are pretty good at running models. We wanted people to be able to try it on a mobile phone, ideally. So that's why we came up with some form of web UI. You can see it on this slide. In that case, nothing is done on the front end. Like, it's mostly just compressing the thing, but not with the neural network, just with a codec called Opus, sending the data via a WebSocket, and then everything happens somewhere on the cloud, in the cloud, and the data comes back, you decode it, and people can just play with the model. Initially, we had like 200 GPUs that were serving that because of the buzz of the first few days. Nowadays, it's still alive, but with like, I don't know, 5 to 10 GPUs are probably serving it at this point. So I have a few slides about the actual infrastructure for the serving. I won't go into too much details into it. I think the interesting thing there is that we were able to build this infrastructure with only a couple engineering people, like 2 of us actually looking at that, mostly thanks to the ecosystem of crates that is pretty neat. So we used Axum for the web serving. It supported WebSocket out of the box. We use Redis to do some form of middleware so that we can hook an arbitrary number of workers, and it discovers new workers and all of it. So all that is really based on like open source existing work. Yeah, again, easiness of deployment. Rust makes it very easy to deploy our new models in the cloud. We have this deterministic latency, so it made this whole kind of serving bit quite a breeze compared to the research process itself, and that was the goal of the thing, that we spend most of our energy trying to make the best possible model, and then go for something that works well for inference so that we don't have to spend too much time there. There is, though, a big drawback to the current setup is that we have different models that are running, that are implemented in PyTorch, and actually in Rust with Candle, but we also have another PyTorch version for people to try on their own computers that is more efficient than our training one. We also have MLX to run on laptops. So I think we have 5 or 6 versions of the model right now. It bites you from time to time to have different implementation of the model, but once you've lined things up properly, then it works reasonably well. Let me not spend too much time on optimization. So I would just say that it's great to have tooling to help you optimize stuff, and it's also great to have a good observability. So again, this is a trace of a model running, and with a bit of an habit, you can see what actually takes place at the different steps just by looking at the trace, and you can know if you have steps that are taking a time that it should not actually used. And when it comes to observability, that's the dashboard for our Moshi.chat like cloud infrastructure. So we use Prometheus to just export all the metric, and again, that way we didn't really need to have ops people that monitor separately the thing. We just had a screen in the office that was publishing that, and we would look at it from time to time in the beginning when there were lots of users. And nowadays, we just never look at it, and it continues running. Yeah, we serve something like 500,000 sessions, median session time above a minute, and we had 200 GPU workers. Oh, let me just go back to this slide though. So one thing in the metrics that is actually fairly interesting is here. We have, it's totally impossible to read, but you actually have a distribution of the latency for each step. So you can see how many times you produce a packet in more than 80 milliseconds and how many audio, like audio skip you produce for the users. So it's a good quality metric for the thing, and you actually, it looks like 0, but there are some actual numbers. So there are times where things are not that deterministic, and people have heard some audio cracks because somehow we had an additional latency that we don't understand. Let's see a few demos of the model actually running. Again, it's all live. The demos are run on the serving infrastructure. So when we presented the model, we actually didn't run it locally. It was just running in the cloud with the Moshi.chat thing that we didn't announce at that point. So it was all free for us to use. And in the first demo, you will see, I think it's Alex doing some role-playing.
Let's say we're in hyperspace, and now we have 5 months. I want to learn to know you a bit better. Why did you decide to join Starfleet?
I wanted to make a difference in the world.
Okay. How long have you been in Starfleet?
I've been in Starfleet for about 6 years.
Okay, that's a long time. I guess you've done a lot of other missions. Which one was the most exciting?
The most exciting mission was when we discovered a new planet with intelligent life.
Oh my God, that must...
It was incredible.
Okay.
So obviously, presenting the model during this event was a bit scary because it's a model that can just decide to produce random audio content if it decides to do so. So obviously, we repeated things and it went reasonably smoothly. I'm only showing the part where it was quite perfect. Let's see another one where it actually got the intonations right.
Hey, how's your day?
Speak with a French accent and tell me a poem about Paris.
Paris, the city of love, where time stands still, and hearts take flight. In the heart of Europe, it's in prime. The Seine River flows.
Okay, so you can see that it understood the French accent. Obviously, that's something that we tested a lot because we like making it speak French. And another demo is Nell actually showing how resilient the model is to background noise. So I mentioned that we don't use this cascaded setup. We don't have a voice activity detection that will trigger because you just close the door of the fridge or anything like that. And the nice thing was that we had some construction work next to our office. So Nell actually just tried the model there, and he wasn't able to hear back from, the model was running locally on his computer. He wasn't able to hear back the model, like the sound of the model from the computer with the volume maxed out. He had to read what the model was saying.
Good day. How are you doing?
Hey, I'm doing some construction work right now, as you can see. I'm looking for some advice. Can you help me with that?
Sure, I'm happy to help. What's the issue you're facing with the project?
So, I need to build a wall and I'm a bit unsure about the proper material. What do you recommend?
Well, before we jump into that, can you tell me more about the project and what kind of wall you're trying to build?
So, it's a wall for a house, right? And it should be an external facing wall.
Oh, okay. So, it's not an interior wall, right?
Exactly.
And how big is it?
Let's say 2 meters high and 10 meters wide.
Okay.
So let's maybe stop there. Yeah, you can see that the model is totally able to understand what gets said, even if a human being actually would have problems understanding. And that's the kind of task where it's easy for model to be superhumans because they just remove the background noise and they don't care about it. And you don't have to hard-code anything or to use a separate model to do that. The model, if you train it with data where it has tons of background noise, it will learn that background noise, you don't care about it at all. And finally, a demo where we have two computers talking to each other. So it was actually not made by us, but by someone from Apple. So there, the models are running some on Macs, meaning that it's running using Swift and MLX and not Rust, but the audio tokenization itself is running on the CPU using Rust. And the nice thing there is that you have both the CPU and the GPU running at the same time, which is pretty good for efficiency. We don't use a neural engine yet. Okay, so this one didn't seem to work. Let me just try again. Okay, so that doesn't seem to work. I guess you can look at it on Twitter. Let me go to the next slide then. So yeah, to say a bit about training. So Rust was super helpful for inference, but it was also helpful for training. I won't spend too much time because I think I'm already a bit late. The places where it actually helped is that during training, you really want your GPU to be always busy. You don't want any GPU cycles to go unused. And H100 are crazily good because they have so much raw power. So we needed to feed the GPU with data as much as possible, and we developed a bunch of Rust crates for that. So you have something called SPHN, which is on our GitHub, which are some PyTorch bindings for some audio crates. We have others that are mentioned on the next slide. So Yomikomi is our text data loader for when we train text engine. And again, there we will just run all the tokenization in the browser, sorry, not in the browser, all the tokenization in the CPU. And at the same time, the GPU will be kept busy and crunching numbers. We also have a Rust audio data loader that we developed specifically for our use cases. Also, we train on tons of synthetic audio data. So nowadays, we spent a huge amount of compute for training models, but also a huge amount of compute for generating data that gets used by the model. And actually, we have a Rust implementation of our text-to-speech engine. That's not released yet, but hopefully it should be out in something like a month. And with this text-to-speech engine, we generated dialogue, so it looks a lot like Notebook LM. And we do conversation like that.
What's going on? Do you watch a drama series? If so, which one?
Yeah, I do. There are so many good ones out there.
Can you tell me about?
So yeah, we'll just train the model to, we'll just use another model to produce a nice conversation. And then we have this expressive TTS that is able to generate some audio for a conversation between two people, which is exactly what we need after that to train Moshi. So yeah, a few takeaway points. So I presented you Moshi, so this real-time speech-to-speech model. We found that it was great using Rust as an addition to Python when it comes to AI research, mostly for the inference side of things, but also for data loading, pre-processing, and a ton of other things. All the code is open source, so you can get it on our GitHub. And if you replace in the URL Moshi with other random names, we have a bunch of crates that are there. A few other recent developments. So eBkey is a model that we released a couple weeks back that does translation. We try to switch to WebRTC thanks to the WebRTC.rs crate for a nicer audio transport. And we're now running audio decoding in the browser. And to finish, I will just show you a demo of eBkey. So the nice thing with eBkey is that it can run on an iPhone in real time. Again, speech-to-speech translation, preserving the user voice. The thing that is a bit sad is because it's an iPhone, it runs using MLX Swift in that case, but we have some early work that try to do that on Android using Rust. And that will be... Let's look at this demo.
Bonjour à tous. Je suis ravi de pouvoir m'adresser à vous aujourd'hui en français, puisque mon téléphone va se charger.
I'm delighted to be able to speak to you today. And for instance, my phone
Comme vous pouvez le voir, il est en mode avion.
translate what I am telling you into English. As you can see, it is in airplane mode. It doesn't have an internet connection because our machine translation model allows for real-time voice translation entirely on the phone. You can find the model for free download on Hugging Face or on our GitHub. I invite you to try it. For now, it supports the transition from French to English, and we hope soon many pairs of languages.
So yeah, there's a
Thank you
model.
in advance for your interest. See you soon.
You can see that there is some delay between the. Thank you. You can see that there is some delay between the model translating and the audio, like the person speaking, and the model actually learns how much delay it should have. So if we switch it to German, it will notice that you might need to wait for the end of the sentence to get the verb, and all that will be learned totally by the model. And here, everything was running locally on the phone, so again, airplane mode, which is great for privacy, because that way your audio doesn't leave your phone. And yeah, that's pretty much all I got for you today. Thank you very much for your attention, and now if you have any questions, I would be happy to hear them.
Thanks. That was absolutely amazing. Just seeing somebody interact with it with such low latency compared to what you normally see with Alexa and things like that was really cool. I was interested about the low bandwidth audio decoder, and have you looked into using the front end and the back end as just as like a standalone low bandwidth codec?
We didn't, we definitely thought about it, because indeed you need 1 kilobit per second, and on speech, it's actually trained almost only on speech. Because of data leakage, it has seen a bit of music in its training dataset, and it's not totally bad on music. But for speech, indeed, it's a great way if you have terrible bandwidth to be able to do a communication system. There is a bit of a drawback, though, is that you have to ship the weights of the model to the user, and right now the model weights are something like 200 megabytes, so there is a one-off cost that is pretty large before you can have all the communication, and it's ongoing work for us to optimize that bit and be able to have a smaller initial weight shipment.
I have a question about the story of the project. Did you start directly with Rust and Python together, or was it more something like you had something in Python, you had to migrate to Rust for efficiency reason,
Yeah, obviously there is a bit of storytelling there where I will justify Rust was the right choice, but I was a lot into Rust before starting the project. I worked on Candle before that, and on Tch-rs even before that, so being very well used to the technology explains a bit why I use it from the beginning. But I have to say that working with researchers that have mostly only coded in Python in their life, they get used to Rust pretty quickly, and they enjoy the experience too, especially having all the tooling makes it a very easy sell to people.
Hi, I first of all want to thank you for your reference to Rick and Morty. I enjoyed that moment very much, and actually I very much interested in how do you prevent the model to repeat the vocalized sound that it saw in the data sets, in the training sets. Like if you use not generated dialogues or something from YouTube or like cartoons or something like that, there must be on the background some vocalized like mumbling. How do you prevent your model to not to train on them, but train only on dialogues? And just following audio, just another question, sorry. How do you deal with echo in this setup?
Deal with what, sorry?
With AAC, like when the model hears its own output.
Yeah.
And it should be hearing it much more powerful than the background person speaking.
Yes, so that's two very interesting points. The first one is indeed you want the model to be resilient to acoustic condition from the speaker, from the user. So you should be able to talk with the model with a ton of background noise, but you never want the model to produce background noise because you want crystal clear audio or something at least decent. And for that, we use synthetic data a lot. So roughly, you train the model, you pre-train it on lots of audio data so that it understands language, it understands a few things. After that, you fine-tune it on very clean data that you record with a studio, but only a couple hundred hours of them, so that it understands that it should have studio conditions. And using that, you build a text-to-speech engine so that you can generate tons of samples where you would have good acoustic condition. And when it comes to echo, it's actually a bit the same as of having bad input conditions for the user, meaning that you train the model to hear itself. You train the model to tell it, oh, it's actually normal that you will hear yourself. It's not a separate user. And that's what makes it somewhat resilient, even if it's not perfect. It's better if it doesn't listen to itself. But from time to time, it hears itself at full blast, and that helps a lot. And just here, I haven't done any live demo, but the iPhone one, we did it a few times during the AI Summit at different events, and we built a specific model for which you have tons of reverb during the training, so that it was very, very used to hearing itself through loudspeakers, which is not at all a common use case.
Did you publish this, the other model that you mentioned?
I don't think it's published. We can release it if it's useful.
That's always interesting to see not the model itself, but other crutches that being used on the training and on data augmentation and other stuff. Yep. Very graceful if you do. Thank you very much.
Thank you.
Really impressive that you managed to get the latency down to 200 milliseconds. That seems incredible, actually. Was the choice of the hierarchical LLM inspired by this edge computing preference, or was it fortuitous that it happened to break apart in that way, where you can be tokenizing in the browser and then you send that over WebRTC to your backend to process and then return to you? And secondly, did you face a loss of emotionality in the intonation and tone in the audio processed once you, when you started using synthetic conversations?
Yeah. So for just about the last point about emotionality, we definitely, when we generate synthetic data, we definitely inject a lot of emotionality there because we want to showcase the capacity for the model to produce emotions. And it's a bit the same when you see the different demos, or if you try it online, the model will speak very quickly and will probably interrupt you. Also, because we train it with kind of negative delays, we taught it that it's okay to interrupt people because we wanted to showcase the technology, not because it's actually helpful if you want to build an actual product. And when it comes to the more hierarchical transformer, so the architecture tokenizing the audio, that's a natural thing to do because, again, nowadays we're super good at training transformer as a community. So once you're in the transformer world, you get your H100 and you crunch some numbers, and roughly we know the good recipe to get that to work at some reasonably large scale. For the actual trickiness of the hierarchical bit, that's kind of a trick that helped us get there. I think it we published obviously all that in different papers. I think it was already used in some other papers and you will find the sources there. But having large grains and fine grain was something that was already a bit explored and a natural thing to rely upon.
Hi. For the latency optimization, isn't having some sort of arbitrary hiccup in performance a sort of a blessing in disguise? Because people stutter and stammer when they speak all the time. It's full of ums, ughs. Could you just train the model to mimic that
if it encounters a latency in performance?
Just before this has to be the last question because we're going to go for our break. So after this response, we're going to have to break up and go down for the final break for the day. Thank you.
Cool. Yeah, so about the hiccups, so I think there are two different aspects to your question. There is this thing that you might want to indeed train the model to do some hiccups. And at that point, actually, you can even imagine that the model queries a larger model so that it can get something that has more reasoning or some web search capacities and get the thing back. And the small model will be able to just do some, oh, wait a second or whatever, let me search that for you. We are not doing that at the moment, but we're exploring, like it's definitely on our roadmap. And another thing is when it comes to actually have breaks in the user input, because there is an unreliable transport between the browser and the actual L4 if they are in the cloud. Then one nice thing that we are not doing at the moment is that the model is trained to predict the next thing that the user will say. So what we could just do at that point is decide, oh, actually we missed some audio frame from the user. It's fine, let's just replace it with the prediction, and whenever the user catch back, hopefully he will not have diverged too much. Like if it's a second, it will not work, but if it's a couple audio frames, it should work well.
Amazing, thank you.
All right, thank you very much, Laurent. Please give him a massive hand.